and I'm really excited to share with you about what I've been working on these past 6 years. So something has really changed about human-AI interaction. We used to be excited about finding objects in images or detecting writing tone, but now these are real interactions, like drafting a little bit of an awkward message, learning about a concept in a paper, proofreading our writing, or even just venting about some drama happening in our lives. But what that means is that an LLM is a personal assistant, a topic expert, a copy editor, a confidant, and so many more things all at once. And I think that's a problem because it's all squished into one interface with an identical input interaction, no matter what we're doing, and we end up with these generic outputs from the model. And I call this a spork problem. By combining many functionalities into one interface, we actually get worse results. Using a spork is maybe not the peak eating experience for you. When you're trying to stab into a piece of broccoli and it's not working, it's because it's also trying to be good at scooping soup. It's not the best spoon or the best fork because it's trying to be both at the same time. And it's challenging to override LLM sporks. I can try engaging in a series of prompts to manually override the generic outputs, but research has found that prompting is effortful and challenging, and even worse, it's a reactive strategy. I can really only first see the spork and then have to react and put in that work myself, if at all. And sporks are everywhere across AI systems the more you look. For LLMs, we see these types of generic outputs, but social media also has these default feed rankings that we see and that shape our opinions. And topic models that help us analyze broad swaths of text have these standard topics that get surfaced. And I think this is really worrying because, when we don't override sporks, we can end up with things like homogeneous thinking across the population when people are relying on the same tool. We can have things like feeds that amplify political polarization and impact our society. And we can end up with really potentially shallow understandings of text that are really important to understand, like public sentiment. But if sporks are so bad, why do we have them in the first place? Well, sporks can be a good thing. They're great for when we don't know the user's situation and goals, and we kind of have to make an assumption. Like if we're camping or we can only bring one utensil, sporks are great for that. But if I have my plate in front of me, I'd much rather have a spoon if it's soup or chopsticks if it's noodles. And similar reasons underlie LLM sporks. At training time, developers don't know all of the user situations they'll be faced with, so they bake in assumptions about many potential user situations in the data and the training processes. And that extends to these post-training processes that fine-tune models against many possible objectives, like many different values or many diverse annotators, preferences, but that can lead the model towards these more generic and spork-like outputs. To summarize here, we have this problem of spork AI interactions, where predefined objectives produce generic interactions. To combat these, my research focuses on just-in-time AI interactions. These enable specialized AI interactions with just-in-time objectives, much like your own cutlery drawer that has the specific tools you need in the moment. To do this, my work focuses on a few key challenges. So we have different types of AI systems out there, like the ones I talked about earlier. And the challenge first is, how do we decide what objectives to pursue? And then second, how do we embed those objectives interactively into AI systems at the time when users are using them? So my work contributes technical methods to address these challenges. First, on determining what objectives to pursue, there's strategies like observing the user in interaction, transferring knowledge from social science, and starting from a steerable default. And just as an overview on the second question, on how we embed these in interaction time in AI systems, there's methods like generator-evaluator architectures that allow us to hill climb on these types of objectives, feed re-ranking methods that allow us to co-opt the objectives of existing systems, and modular algorithms that expose their objectives by design. And these different methods unlock new and specialized AI interactions. So for example, for LLMs, because we're able to generate these distinct user objectives, we're able to unlock the generation of proactive tools and interfaces. For social media, when we embed these types of societal values deeply, we can do things like reduce partisan animosity for thousands of participants. And when we're looking at topic models, when we have these types of steerable concepts, I'll show how this enables researchers to analyze their own data and publish novel research. And so we're really thankful that this work has been well received by our community, and we've seen adoption from open source releases of this work that have led to other follow-on work by our own team and other researchers, and opportunities for new funding as well as usage by industry teams. These ideas apply also across the AI lifecycle, not just at the time when we're interacting, but also upstream when we're thinking about designing and developing AI systems, training and fine-tuning, as well as doing things like evaluating and auditing. So for the rest of today's talk, I'll talk through a few end-to-end examples of this. First, showing how just-in-time approaches can really yield new interactions for individual end users, but not just lay users, also domain experts who are using AI. And not just individuals, but also impacting society at large. And then I'll share the visions that shape my future research agenda. So I'll jump right into the namesake just-in-time objectives work, which is designed for everyday end users. And this work appeared at CHI earlier this year. The main issue, as I talked about earlier with sporks, is that we don't know what specific tools to build in advance. Our insight here is that we can wait until interaction time when we actually have many more cues. So let's take a paper talk that I was working on. At interaction time, we can actually observe what a user like me was doing. So even from this one screenshot, we can tell things like which of these papers this talk was based on, that I likely need to finish the slide outline given that it's half done, and that this course that I'm speaking to is one that has many undergrads, such that we can infer a quite detailed objective like this for the system without any user effort. And that's what we call just-in-time objectives. They're a model of the user's in-the-moment goals that's automatically induced by observing their interactions. And importantly, that allows us to then optimize LLM systems on the fly towards this type of more specialized output that users might prefer, whether we're looking at generating whole tools or individual chat feedback. So for reference, when I was working on those same slides and went to ChatGPT, I provided some rather generic forms of assistance, and I went and did a long back and forth set of prompting to give the context and get the help that I wanted. But from that same slide deck, JObjectives enabled specialized assistance, like a slide outlining tool that had already suggested the relevant talk formats for my audience. It generated a slide outline that had elements I could easily move around, given that the structure was the main focus at this moment, but also with an edit mode in situ where I could refine the content as that was the next step. And I got all of this without needing to prompt or engage with the system. JObjectives allow us to automatically specialize LM output from the start and generate this type of software on the fly. So for example, in another case, when I was working on a diagramming tool in Figma, it generated this, or when I was working on a diagram, it generated this custom diagramming tool that had a canvas and nodes that were based on the specific concepts that were in my paper that I could move around and edit. It had different automatic layouts that I could experiment with. And it also had a targeted LM feedback on these versions that I was generating, again, without me needing to request this directly from the system. So that's the interaction that we're striving for. But to make this happen, we had to deal with a few technical challenges. First, how can we induce accurate objectives? We have as our input a user who we can observe, and we want to get out these sort of objectives like I showed earlier. And we find that we can get more accurate objectives by prioritizing a wider compatibility with a broad range of observation types, but those that are less effortful to gather. These are ubiquitous inputs like screenshots of the workplace or the raw DOM of the web page that we can increasingly make sense of with modern models. And this task also becomes more tractable when we explicitly bound our objectives, focusing on instantaneous moments when we might be able to better capture what a user is doing, but where we can also have the LM state its uncertainty and have our pipeline reason over it very concertedly. So with these principles in mind, Our JIT objectives are induced by a language model prompt on an input of an interaction trace, which could be a screenshot of the workspace or a stream of screenshots or the DOM of the web page. And the model focuses on instantaneous objectives based on that trace. And this produces these rather lightweight JIT objectives that have a name, a detailed description, and a weight. To understand whether this process actually yields accurate objectives, we ran an experiment with over 200 online participants who uploaded screenshots of their own tasks, just things that they were working on. And these really spanned a wide range from a draft letter to the UN to running statistical analyses. And from these, we had our system induce JIT objectives, and those are things like completing country-specific recommendations in the UN letter or analyzing specific statistical findings in the Excel sheet. And across these tasks, we found that JIT objectives were highly accurate. The vast majority of these objectives were deemed by these participants as accurate or very accurate. But I'll note that there's not just one valid objective at any given point in time. So we also ran a task where we surfaced the top 3 objectives in a random order. Users could also write in their own custom objective. And we found that induced objectives were chosen in about 98% of cases, and that user preferences promisingly were aligned with these induced weights. So the higher weighted options were more frequently selected. So this is really promising, but there's then the question, are these actually good for anything? How can we actually have them be a generalizable way to specialize this broad range of AI systems? The challenge here is that there's so many different types of LLM systems. Beyond UI generation that I was talking about earlier, there's things like expert or role generation, coding assistance and writing assistance, and general purpose forms of assistance that you might see today. But when we look across these, they're made up of some similar building blocks. There's some sort of prompt coming in from the user, of course, and there's generators that are responsible for producing some type of artifact, whether that's a specification for a UI or a plan for writing code. And often there are evaluators in the loop that are judging this content, like LLM as a judge scoring or open-ended feedback that's used to iterate further on further generations. Our JIT objectives can replace this first step by automatically inducing what a user needs rather than strictly requiring their prompt. And then once we have that, we can use this JIT objective to steer the existing generators and evaluators irrespective of what they were meant to generate. And this can be as simple as appending the JIT objective to existing generation and evaluation prompts that might already be internal to a system. So if I consider a system that's generating feedback, it might be powered by some detailed system prompt that has criteria like principles and a custom chain of thought process. And if I have a slot instead for the JIT objective that can be added to this prompt, then in real time, as the user is interacting, it can tailor this generation in this more strong direction. And similarly, if I have these components that are evaluating content, they might have this detailed prompt that has a detailed scoring rubric, and adding this JIT objective allows us to refine the evaluation on the fly, not just scoring by general quality, but getting much more stringent. Taken together, this produces a generalizable architecture where we can take in an interaction trace, have a language model induce a detailed JIT objective, and then steer existing generation and evaluation operations to produce specialized output. I want to note here for a second that we were able to implement this using third-party models, which means that we're not maxing out our AI systems that we have today. Just by focusing on improving our objectives, we have this headroom to really raise the performance of even off-the-shelf models. But JIT objectives can also help us train new models. So we've been operating here at the end at inference time, but some of my other work has been upstream at the training and fine-tuning phases where we can get stronger shifts in model behavior. So just as a quick preview, for example, I worked on the Ditto project co-led with Omar Sheikh and Joey Hena, and we developed a technique to fine-tune a language model to a distinct user style just using a handful of demonstrations on the order of 5 writing samples. And by iteratively treating the user's demonstrations as unilaterally better than anything the model generates across time steps, we're able to produce much better and more user-aligned behavior from the model. And this shows us that once we have the right objective, Methods like this can strongly steer a model and bring performance benefits even above manual prompting. But we wanted to see how effective the prompt-based interventions would be with these JIT generators and evaluators. So we returned to that same set of data from the online participants that I showed earlier, and we surfaced back to them this task where for generation, we had these baselines that they took in the full screenshot that the users had provided and suggested relevant experts to assist with the task, tool designs, and feedback to directly assist on the task. For example, here we had a TA training handbook where you can see that the generators provided some general forms of assistance for this task. And the JIT generator was the same, but just with the induced objective added. Here, the objective actually picked up on the fact that there was unresolved comment about clarifying the role of a TA on the handbook, and you can see how the outputs here are tailored accordingly. We find that with this small modification over the baseline, JIT generators produce outputs that are preferred about 70% of the time in head-to-head comparisons. And looking at the evaluators, we find that if a JIT evaluator is working well, it should be selecting more user-preferred outputs or more user-preferred candidates even among those JIT generations. And so that's what we did here. And we'd want to see a higher win rate for a larger number of samples. And we indeed find that JIT evaluators help us to select more user-preferred outputs, further hill climbing on this objective, jumping up about 16 percentage points from 10 samples to 1 sample, which is almost as much benefit as scaling up to a whole order of magnitude more samples. Putting these together, we built an interactive system called Poppins that demonstrates JIT objectives with on-demand UI generation. And we had this in a browser extension. With my presentation open in my browser, I can initiate Poppins. And based on that same screen I showed earlier that had this pending structure, it induced an objective of improving the presentation structure. But there's other options I could provide that I can select from or modify myself. And then it suggested tool ideas like a presentation flow organizer or a research narrative validator. And each of these has a detailed specification about how the tool ought to work. Again, I can go and modify these details if I want. And then the system generates code on the fly and renders it for me here, which was this interactive action plan from my research narrative. And it suggested things like framing the problem statement around examples the students could better relate to, suggesting generated tools from the paper that might be more compelling to demo. And again, we got all of this without me needing to go in and prompt. And maybe I didn't even think at the start that I wanted to switch over to ask a model for help on this task, but it went ahead and assisted me. And we wanted to understand then how JIT objectives actually work in practice with Poppins. So we ran hour-long in-lab sessions with 17 participants who brought in their own writing tasks. And this was really important to us that these were actually tasks that people were working on and cared about. So people brought in a range of things from short stories to scholarship applications. And Poppins produced outputs that were rated as significantly higher quality than that of a baseline language model, something very similar to an interaction to ChatGPT that participants often were already using. And I'll walk through a few of these examples. On a participant's short story draft, Poppins created a tool that helped them to track the trajectory of characters' emotions over the course of the story, and that actually helped the author to realize that there were some inconsistencies in how their character was coming across that they wanted to go in and fix after the study session. In a pretty different setting, there were participants' research notes, and Poppins created a tool that helped them to explore different technical methods that they were weighing, looking not just at the algorithms and code, but also the applications downstream to help them compare. And these tools really varied in form. I won't go into depth here, but there's things like thematic highlighting and diff views to help manage the language of a presentation. And yeah, we saw quite a range across these participants. But what I found interesting beyond the artifacts was how they changed users' processes. We found that because JIT objectives were sufficiently accurate, they reduced user effort, having them focus not on, for example, the type of feedback, not on prompting the language model, but focusing on the type of feedback they wanted. And it provided a helpful starting point where it's often hard to go and articulate your goals to a system. And they also ended up actually improving the ultimate task performance. We had a participant who was already very familiar with ChatGPT and had used it during their work, and they were surprised that they actually got higher quality outputs out of the system, out of the box, even on par with advice they had gotten from their real-life advisors. And I think promisingly, users found that this assistance could augment their abilities, really stretching what they're capable of doing rather than replacing them. In ongoing work led by PhD students Michael Ryan and Dora Zhao in our group, we're finding that J objectives can extend. For example, they can take on project-level scope, enabling background agents that might unblock your trajectory, and they can extend to long-term needs. We can steer AI agents by inferring users' underlying motivations. For example, if a user has a love for learning, but also many parallel commitments, the right assistance might not be to autocomplete as we might do today, but to actually help them rebalance their schedule to set aside that time for the learning they want to do. To summarize this work, end users often don't know exactly what they want or maybe how to articulate it with AI systems. And J objectives address this by inducing specialized objectives on the fly at interaction time. And I think the idea here is that we can really meet users where they're at and raise the baseline of where they're starting from when they choose to interact with an AI system. And I'll show how similar principles apply to domain experts. Just-in-time objectives are also relevant to tasks that we might not think of as involving personal taste, like analyzing data. But I think one evidence of this is that we developed and open sourced a system as a Python package, and it's been adopted by a number of researchers in academia and industry. And I think there's appetite for text analysis that is steerable and interpretable by design. So the vision of topic modeling is that we can go from messy text data to meaningful findings. And this is an old problem with work spanning over decades in this area. But today, no matter what my interests are as an analyst, the topic model returns the same set of generic themes from the data set, and they're often hard to understand because they're so vague. We introduced concept induction, which is an approach for surfacing high-level concepts from unstructured text, where our goal here is to make the default output steerable by design. So instead of vague keywords, concepts are natural language descriptions like government accountability, and they're defined by explicit inclusion criteria. And that means that you can understand the default output, but you can also go and turn it around and steer it based on your specific interests. So maybe I'm interested in federal government accountability, or maybe I actually have a different definition of accountability that I go and want to insert. To achieve this vision, we developed an algorithm called Loom that's made up of some modular operators that we can apply iteratively. And I'll just give a bit of an intuition about each of these operators. The synthesize operator is the most important. It's taking the key text from the documents and drawing these unifying concepts across them using a language model. For example, here extracting concept about energy solutions. But you'll notice that the input here is really critical. If we don't refine these, we can end up with really broad and uninformative concepts that are unifying them. Working backwards, we have two operators that basically set this up for success. The distill operator basically addresses the fact that not everything in every document is important. We want to really be able to zoom in to the parts that are relevant for our analysis. So the distill step uses a language model to extract key quotes and abstractively arrive at key points. And the cluster operator allows us to make sense across these undifferentiated pool of key points and identify cross-cutting commonalities. So we detach the key points from their documents and then recluster them using embeddings and HGB scan so that we can have likely more related text spans together to be passed up to synthesize. The distill cluster synthesize steps that I talked about earlier give us these candidate concepts. And the score operator allows us to go and verify whether these concepts actually occur by independently mapping back to the documents. And so that helps us verify whether and where these concepts occur. Now, because we have these modular operators, we can steer each of them. The seed operator allows the user to steer any operator using a seed term that modifies what it attends to. So seeding the distill step guides it to take notes on only the parts of the document that are related to the seed, or seeding the synthesize step has it propose concepts that are related to that seed. So in summary, all these steps in the distill, cluster, and synthesize phase propose these concepts iteratively. The score operator allows us to go back and map these to the documents, and then the seed operator allows us to steer this whole process. We built a text analysis tool around this concept, allowing us to visualize data sets in terms of steerable concepts. And I'll show how we can use it to analyze a data set of political social media posts. We have a main matrix view here where we can see all the concepts that were generated by Loom as rows. And on the columns, we see metadata, like here, partisan animosity ratings. And analysts can hone in very quickly on unanticipated trends. Like there was a benign looking concept of political party positions that had high partisan animosity. And based on the inclusion criteria, we see that it's capturing the actions or positions of political parties. And there's a summary and representative quotes and all the documents down below. And what the analysts found was actually that they're written from one party's perspective and are critiquing the opposing party's stance, not just talking about their own position. So that was what was going on here. But it also helps analysts to investigate nascent patterns. Within this policy-related concept, there were posts that were discussing policy outcomes as a crisis. And the analysts created a custom concept called crisis based on what they were noticing, and were able to rapidly isolate more posts that were displaying the same behavior. I'll just go through quickly here, but comparing to status quo methods, as I mentioned before, there are existing methods that produce things like vague keywords, and even emerging methods of just passing to an LLM can work all right for capturing generic concepts, but these are things more like transportation policy, where we find that Loom is able to actually recover more specific concepts, things like economic stability that might characterize what's happening within a broader concept like economic policy. And we ran a series of evaluations with synthetic data sets that allowed us to verify that this pattern held true. But I've been particularly excited about what this has enabled after this project. As I mentioned before, we released this as an open source package for data analysts in their notebooks. And we created some documentation and guides to try to make this accessible beyond the paper. And this enabled researchers to lead their own theory-driven research. Here are just a few examples of research that's been published at places like EMNLP and IEEE Viz. And these include things like understanding the impact of public science communication, methods that could help us better conduct literature review, and discourse strategies that are used by populist politicians. And researchers also applied Loom to a really wide variety of types of text, even things we didn't anticipate, like visualization notebooks and product reviews. To recap this work, domain experts often really do know what they want, and they seek control over the process. Loom is designed around a steerable default. Its modular operators and its output are intended to be steerable so that users can adapt them just in time based on their analysis objectives. And this has unlocked some novel scientific research. I'll now talk about how this can speak to AI in society more broadly. Just-in-time AI isn't just about individual users. It also applies to social computing systems like our social media feeds with many users. And we found that to tackle these types of broad social outcomes, we often need to push against the default values that are embedded in these systems. And this can be really powerful. This work opened up new lines of research, including a science paper, and it led to funding for more work on rethinking the default objectives in our social media feeds. And I think there's been some excitement because there's significant challenges with moving beyond the individual user setting. So we were interested in this setting of social media and democracy. As you all know, social media plays a really central role in our lives, and there's been increasing concerns that social media is harming democracy. There's been increasing evidence that it's associated with increases in partisan animosity, these negative thoughts, feelings, and behaviors towards a political outgroup. And a major problem is that social media AIs today are centered on the wrong objective, a generic objective of engagement signals, such as likes and clicks. But threats to democracy don't yield observable engagement signals to train on. There's not a trace when a user sees a post that lowers their opinion of the opposing party or reduces their trust in a practice like voting. And it's technically difficult to instantiate an alternative. Even if I know that I want to reduce partisan animosity, how do I go and do that as an individual user? I think a challenge here is that we have this broad set of social media posts and inventory out there. And our output that we want to arrive at is this social media feed that we ultimately see. But the actual outcome we care about is not that feed, it's the level of partisan animosity in response to that feed, this behavioral outcome, and that is harder to anticipate. We need to develop methods to address this. Well, political scientists are, of course, experts about threats to democracy. Could we draw on their expertise? For example, a recent mega study published in Science had major results on reducing partisan animosity. And they looked at things like interventions such as videos and educational activities. And in that work, they defined a construct of anti-democratic attitudes and partisan animosity, or APA, and that was used to assess these behavioral outcomes. And there's a lot of detail here, but the construct had 8 dimensions that were things like opposition to bipartisan cooperation. They each had a definition and associated survey measures. And our insight was that the precision and detail of these survey measures and qualitative codebooks in social science was really well suited to translate into large language model prompts that we can enact today, where we can take the variable name, the definition that was drawn from the prior literature, and detailed codebook factors that were generated along the way by these expert annotators. And that means that we can take constructs like APA and directly use them as AI objectives, like in our social media feeds. Our work introduces societal objective functions, which is a method for translating these types of social scientific constructs into AI objective functions, where first we identify a relevant a social science construct, like the APA construct, and then we operationalize these into a manual intervention, first allowing us to assess whether this intervention is effective in reducing or in producing the behavioral outcome we're interested in. And then we scale this up with algorithmic methods, like using a language model to re-rank social media feeds. To briefly cover the technical implementation, we had an LLM pipeline for feed re-ranking that allowed us to take in an arbitrary inventory of posts and then generate ratings for each of the individual variables of the construct. And then we can combine these into a total score, use those to re-rank this inventory of posts. And notably, this pipeline is something that can be run in real time if we connect to users' feeds. It can be adjusted to swap in different variables, different rating scales, different aggregations, and ultimately different rankings of the feed. And this allowed us to basically run some experiments to see if we could move the needle on this really important societal issue. So we designed several feed algorithms that incorporated APA. And we also implemented baselines that represent more of the status quo today. So the main conditions that I'll talk about were a downranking feed that put these APA posts more towards the bottom of the feed, and a baseline engagement feed that ranked posts more similarly to how we see them today, with high engagement at the top of the feed. And we ran experiments on US partisans with engagement feeds, manual feeds, and feeds that were algorithmically generated. And the x-axis here is partisan animosity, where higher value is greater animosity. So we're trying to see reductions. And as expected, we observed substantial partisan animosity with the engagement-based feeds like the ones we have today. But we found that manually re-ranking feeds using this APA objective significantly reduced partisan animosity, both for Democrats and Republicans in these pre-registered experiments. And we're somewhat surprised because this is a challenging metric to move, especially with such a short feed intervention. I'll go through quickly here, but we basically found that we can use language models to replicate this type of annotation to a fairly high degree. But the question remained, does that actually produce the same behavioral outcome when you actually use it in a feed? So we returned to another set of experiments where we implemented this algorithmic LLM re-ranking. And we found that we were able to also significantly reduce partisan animosity with this intervention, with both Democrats and Republicans. So this was a really exciting result for us because it means that we have a chance at actually moving this measure out in the wild, because an LLM-based intervention can scale up to many users. And so I'm really excited now about what's possible. Field experiments run by amazing colleagues translated societal objective functions into real users' X feeds with a browser extension. And they confirmed that in the wild, decreasing or increasing APA exposure shifted partisan animosity. And this work was published last year in Science. And other exciting work has shown that we can expand beyond our demonstration of this one value of democratic attitudes. We can expand to a much larger library of values, and that users might be able to control themselves. To sum up this work, for pressing societal issues, we might know what we want to achieve, but we might not know how to achieve it with our existing systems. And I show that transferring knowledge built up in the social sciences can allow us to operationalize these societal objectives and realize them just in time in users' feeds. Zooming out, I've shown how just-in-time objectives work across a variety of different problem settings, from end users who are working on their own projects, domain experts who are conducting research, and communities of users on social media. And I've shown how my research develops strategies for combating these spork AI interactions by determining what objectives to pursue and how to embed them interactively in AI systems. And this came with a toolkit of strategies for deciding what objectives to pursue, from passively observing to transferring that social science theory, and methods to embed these objectives, from LLM systems to social media systems. And these really form the foundation of where I want to go next in my research. As I talked about at length at the start, sporks are bad, but I think there's paths forward. Instead of sporks, what I'd like to envision is instead more like a Mary Poppins bag. This was a magic bag that she always had that had the right tool for the task at hand. So here she's pulling out this really large mirror because apparently the first one was way too small, and now she's much happier. I'd like to argue that this is a vision of user-owned AI. It's a technology that we own and curate. It has many functions available, but importantly, it only surfaces the specific one that I need right now for me. My research vision is for this type of user-owned AI, where everyone can own their own Mary Poppins bag that specializes for them in real time, and not just towards immediate goals, but towards their longer longitudinal user goals and broader societal goals. And this line of work really means that we have to rethink how we design our interfaces, how we structure our own research, and also how we govern AI systems. And so I'll start first with our interfaces. Interfaces today are largely rigid and predefined, and I think that's why we see AI sporks everywhere. I envision just-in-time personal computing with computers that mold entirely to us as we work, where objectives might be these more universal routers to different adaptive computing environments that could be generated and adapted on the fly, addressing goals of varying scope and kind. Like, there are goals that are common to a domain, like making sense of paper reviews that I'm getting. But there's also goals that are specific to an individual, like triaging areas of concern based on my specific research taste. And there's competing goals within an individual, like in a busy week, how I prioritize revisions among many other to-dos. Immediate goals might imply automating tasks that AI can confidently complete. But if we discern longer-term user goals over maybe months of observation, like investing in health goals amidst a busy research workload, AI might automate the tasks that are most disruptive to my health. Or drawing on societal objective functions, we might have goals like preserving a healthy democracy, and we might want AI to automate tasks that are getting in the way of my civic duties. And I think we can take AI research and not only make it accessible to end users, but go in the other direction to advance AI research. If we consider the full set of tasks like these dots on the screen of tasks that users are pursuing, current LLM logs only really have visibility into a small portion. And they're often only using AI on a small set of tasks that are useful to them, with limited ability to raise problems and maybe even less ability to propose their own solutions. How do we expand this? Here, I envision an AI interaction observatory where infrastructure like automatic pipelines might allow us to learn from large-scale end-user objectives, where we can group by combinations and trajectories of objectives that allow us to understand commonalities not just in what users are doing, but why. And this could power new dashboards that allow us to discover tasks and problems, as well as solutions for AI research to tackle. Finally, on governance, if we want user-owned AI, we need infrastructure for users to actually own these systems and govern them. And this is both a technical problem, but also an interface design and social computing problem. For example, we can already fine-tune models, open models, with a handful of examples like I talked about earlier, but there aren't many end users who are doing this. So it's not just a technical problem, it's also a usability one. And I think JIT strategies can make these more usable. We could build systems that automatically fine-tune models for frequent user objectives that are occurring and learn how to manage and serve those models in the background on a user's device. But fine-tuning may have its limits, and so we might actually be able to get better model performance by pooling resources. And I think the AI interaction observatories could actually help us here by identifying salient communities of users who actually have similar needs but may not be connected. We could design protocols that allow users to share data and compute with trusted community members to improve model performance. And here we also may be able to tackle collective goals. This requires tools to allow us to deliberate over what society-level goals to even set. Like in some of my past work, we simulated juries of community members. Could we assemble juries for setting these types of broad objectives? And we also need tools to embed and monitor these types of societal level objectives. Drawing on the societal objective functions work, how could we understand how societal values not just work in social media, but across the whole surface of different computing environments that I encounter? My PhD work was made possible by collaborations with faculty and researchers across institutions and across areas. And I think this will be really necessary as I tackle this future research agenda. And I've worked with an amazing set of PhD and undergraduate students who have been fortunate to collaborate with and mentor. To close, you should now know how to spot a spork and why it can be deceptively dangerous. And hopefully now you know about the just-in-time strategy, which allows us to avoid predefined assumptions and shift the control closer to the end user. So for the next flashy AI system that might come out, I hope you can ask, is this a spork? Who designed it that way? And what assumptions are encoded by that decision? And are there other ways to build that might give users greater voice over these assumptions? Thank you very much.
The lovely analogies of spork and Mary Poppins bag. I have this question. So one of the practices that, maybe for the future research, one of the practices or multiple practices that have not been included have to do with adversarial situations, where they happen in professional services, such as law, maybe finance, risk underwriting, also defense. But my technical question would be, do you think your research has enough fidelity for human decision making? So by fidelity, I'll just explain it from the analogy. So in computer science, we have byte packing and bit packing, etc. So by this fidelity, I mean there is let's say retinal variables that a person can understand and see when they're making decisions, and the interfaces that this study has done has to do with checkboxes and pieces of text and drop downs, etc. Do you think that in the future research we need to go kind of even one level deeper into retinal marks to mention
I mean, I think these ideas have broad applicability. I mean, we're talking about these types of interfaces that we're dealing with, but if you have AI systems that are acting on any layer, whether it's like low-level computer systems operation and assisting on that, or helping someone on a security problem, I think it's really critical to understand what are the assumptions that are embedded in that AI system that's assisting you. And it might be assuming, for example, that you care about, I don't know, individual security or something, but not like, I don't know, a whole organization security, or maybe like cross country, I don't know, concerns. And I think no matter what context you're in, it actually does really matter that you have similar types of tools. So I think the systems I'm demonstrating here are really like a demonstration of what you can achieve, but I think there is still a broad applicability to any AI system that we might be using, whether for computer science tasks or interface tasks.
I have an easier question for you, Prashant. When you were soliciting tasks for your just-in-time system, did you refer to AI in your request, or were the users primed in any way to be getting tasks that would naturally lend themselves to use of an AI system?
Yeah, I mean, here we asked users to contribute tasks that they were actually working on. We didn't tell them what was going to come afterwards or anything about our system. In those technical evals that I talked about at the start, they were asked to basically provide a screenshot of some task they were working on. We did have a system that like verified and made sure that like it was a valid screenshot, things like that. But yeah, we tried to keep these requirements as loose as possible so that we wouldn't get sort of like easier inputs, and we wanted to basically have something as ecologically valid as we could, because we really wanted to see like, does this approach actually accurately induce the objectives that people have in their tasks out in the world? And yeah, so that was a sort of fundamental like requirement, I guess, going into our study setup.
I have two questions. Maybe I'll give you both, and you can decide which one you want to answer. So, in one of the studies with the algorithmic downranking versus a manual downranking, you had a better result with the algorithmic downranking. I wonder if you is that true?
Yeah, I'm not sure if it's significantly better.
But it looked pretty like pattern-wise. It looked, and I'm curious if you have a hunch on why that might be the case. Okay, maybe I'll give you the second question.
I guess I wouldn't. Maybe I feel hesitant to lean into the why because it is rather exploratory. That difference, like between algorithmic and manual. So, I mean, one possibility is like we did sort of like tune our prompts to like a development set, and it's possible like the development set like I guess maybe like has some attributes that are like I don't know maybe more particular that like language model was better able to hone in on than the manual raters who maybe were thinking more broadly than beyond that set. We didn't apply that same system, like we applied it to a new set of data to do our evaluation, but maybe that could be a potential factor on that first question. Yeah.
I think it's super interesting to see what are they different.
Yeah. Oh yeah, sure.
The second question was about homogenization of output, and I feel like your work is such a great example of how we can move beyond this homogenization effect. And I'm wondering if you think that JIT objectives might actually be homogenizing at a different level, like broader categories of people, or do you think it can actually, I don't know if you can reflect on that.
Yeah. I think actually my ideal world is that people have ownership over these JIT objective induction processes themselves. I think what we're really trying to open up is like, hey, there is a task that exists here, and that too is something users need to be aware of, that they have visibility into and are able to intervene on. Because I think this method was just exposing that there can be sort of this lever up here, and we want to show that to users. But I think it would be a real risk if we just had users use our version of the system and it always induces their objectives, because that may encode biases, for example, towards tasks that a language model can understand, or tasks that are well scoped and bounded and able to be tackled with the solutions it can propose. So yeah, I think it's really an entry point into like allowing us to think about and support a broader space of like ways to induce objectives and act on them.